looking for people. Yeah, okay.
Yes, so let's start our new session, and speaker today is SISSA, who will tell us about asymptotic solutions of our issues, non-meromorphic.
Yeah, thank you. So, first of all, thank you very much, organizers and the group of mathematical physics for invitation here. I'm very happy to be back in Lisbon. Today, I'm going to talk about this. It's a joint work with Giordano Cotti and Davide Massoyer. And the motivation came exactly from the differential equations we saw a few days ago in ODE-IM correspondence. So anyway, let me first start with some motivations for this. First motivation, which was not the original one, but let me say that if you consider a system of differential equations with meromorphic coefficients, actually I will concentrate here to the point infinity. And here R is an integer which is called Poincare rank. And this matrix here is holomorphic for, let's say, on CA, which means the complex numbers with absolute value greater than some positive number A. So in this case, Z equal to infinity is an irregular singularity, and we know very well that we can write formal solutions for this equation. This is a long story, but this goes back to Fukuhara in the 30s and 40s. And then it was more made more systematic. Essentially, everything is in Fukuhara, but it was made more systematic later by Shibuya and by later in papers by Balser, Yurka. So we all know that there are formal solutions, and a general result is that for any sufficiently small sector S at infinity, so let's say sector infinity, there exists at least one fundamental matrix solution. This system, this is an n times n system, which is asymptotic to the formal solution when z goes to infinity. So this is very well known, but we have some problems here that, except for some generic cases, such that the case when the leading matrix, the leading term of this matrix at infinity has pairwise distinct eigenvalues. So in general, we can only say that the sector is small. We can say what is the minimal sector. Yeah. But not how much we can extend it. And the other problem is that this Y is not unique. So the question we ask here is to give sufficient conditions such that we can find actually not the minimal, but the optimal sector. The optimal sector where the asymptotic behavior holds, and on this sector, we would like to find sufficient conditions such that, corresponding to the formal solution, the fundamental matrix solution is unique. So I stress that for generic cases, we know this answer. And also, if we apply the standard procedure by sharing transformations and so on, that you can find, for example, in Shibuya and so on, case by case, we can give an answer to this question. But in general, we don't have a theorem. We don't have a theorem which gives you automatically, given the equation, the optimal sector and tells you if on this sector the solution is unique. So the second motivation is differential equations like the ones we saw a few days ago, also yesterday. So I write this in more generality. So let me write in this way. Finite sum from 0 to some integer h of some diagonal matrices, which maybe depend on parameters, z to the power k, plus, say, some additional term, which would be a perturbation. And so what is this? So these are diagonal matrices. And they are holomorphic with respect to some parameter omega in some domain in, let's say, CM. The important point is these beta k's are real exponents. So they are not rational exponents. They are not integer exponents. And we can order them such a way that 0 is greater than b1, like this. R is a perturbation, small. So we can make this precise, but let me just say, for example, that this R behaves. So this, again, is holomorphic. So let's say with respect to the parameter and also on the universal covering of this CA. So R is a perturbation. I will not be precise here, but you can imagine that this behaves uniformly with respect to the parameter, like something like this, 1 minus 10. So the problem is again the same. So also in this case, we would like to say prove a uniqueness result. So prove okay. Let's find asymptotic solutions. When z goes to infinity. And give sufficient conditions such a way that they are unique on some optimal sector. So you understand that in this case, there is no formal solution. So as far as we know, this means that we cannot apply this Shibuya, Fukuhara, Shibuya, Basel, theory. So Fukuhara, Shibuya, and so on. This does not cannot be applied, and also we think multi-summability arguments cannot be applied. The only thing we can try, and that what we did, the idea was to apply a Levinson time approach. Levinson type approach. I will explain, which allows you to find asymptotic solutions to this equation. But unfortunately, the original formulation given by Levinson, and I think it was 42, paper on Duke, Levinson actually could not prove uniqueness and actually could not even give an optimal sector. His result is essentially along lines. So these are the two motivations, and essentially the two motivations. So let me, first of all, read the main result before I try to answer these questions. So the main result is the following. So we consider a system of differential equations written in the following way. I will not consider parameters today. Because we did everything with parameters, but if I put parameters, everything becomes more complicated. So let us forget parameters. Okay, so first before I say what are lambda and r, let me give some preliminary setting. So we are working here in C star, or on the universal cover C star. And in this universal cover, which I cannot draw, but let me draw just a projection, let me define a plane, an half plane. So first of all, let me just draw a picture, some naive picture. So suppose this is a very nice picture, but suppose I have a real number, R, which determines a direction. So it's somehow an angle. And so this point here will be the point, this distance from the origin to this half plane is a positive integer a. And this point here will be a to the exponential of square root of minus 1, 5. So I define this to be an half plane, which I will call h phi a, and to give a formula. So this will just be the points in C13 such that the argument of z is in the open interval. I use this notation for open intervals between phi minus pi over 2 and phi plus pi over 2. So the argument of z is between pi plus pi over 2 and phi minus pi over 2. And the absolute value is greater or equal than a over cosine of phi minus argument of z. So what does this mean? It simply means that this line, which is actually oriented with a natural orientation, this line is exactly the line where the absolute value of z is a over cosine of phi minus argument of z. It's a simple exercise. And so all the points above define my half plane. Another thing I need as a preliminary is the following. So suppose I take an interval for this phi. So an open interval which has some boundaries, a minimum value of phi and a maximum value of phi. And then I consider the union of this. So if I want to draw a picture of this union, the picture is the following. So again, a very naive picture is the projection over C of something which is in the universal covering. So I have some minimal value phi minimum and a maximum value phi maximum, and what I'm considering is just this domain here. This is the preliminary. Now let me go back to the differential system. So we consider a differential system like this is an m times n differential system, where the matrix lambda is diagonal, and it's holomorphic on some h a. And R is also a matrix. So it's a matrix, which is again holomorphic. So it's a holomorphic matrix. Moreover, in order to go to these equations, we have some general assumptions on the matrix R and lambda. So first of all, R will be a kind of perturbation. Okay, it is better to start from R. R will be a perturbation. I mean, it will be a small, somehow small. This can be made very precise. I don't know if it is the case to give the complete definition. Maybe at the moment not. But you can imagine again that this behaves something like, for example, like this. We can give a very precise definition of what we mean small. Actually, this in our paper, this was called good decay condition. But maybe now it's not necessary to give exactly the precise definition. Today is a good day, but yes, thank you. So you see, mine is very strange. it works very strange. This two decay condition can be given very precisely, but maybe at the moment is not so important because I'm not going to prove all the details of the theorem. But the very important point that I have to state precisely is what is lambda? This lambda. So this you understand will be for us somehow a perturbation with respect to lambda. And lambda, if you look at the system without R, you can immediately solve this differential system because lambda is diagonal. So there is a solution which is something like exponential between some z naught and z lambda t. This is a fundamental matrix solution, say, to the unperturbed system. Okay. Okay. So actually, this exponential will play a role in everything in asymptotics, as actually we are already somehow used to. And so let me say what are the conditions on lambda. So before giving the conditions, it's necessary to define some objects. Sorry for this, as maybe this is the most technical part of the talk. So this J stands for a compact, well, a closed interval contained. Okay, so now in this extended half plane, I can consider lines. Let me call this line L phi B. It means that this line is identified by, this picture is not very generic. Let me take a line like this. So this is identified by the angle phi and by the distance here, B. We can write, of course, the same equation like this with B here equal B. So now consider along this line, take 2 points. So there is a natural orientation on this line. So let me take a point W and the point Z. Considering this natural orientation, actually, I can also say that here there is some infinity minus and infinity plus. Anyway, let me construct the following object. I consider the real part of the integral between W and Z along this line, L phi B, of lambda I, the entry I minus lambda j dt. And then I take the sup. I take the sup for all W's, all points, W coming before Z. And then I also take the sup over all B greater than A and over all phi contained in J. So this is what is this object here. And the same, this one is exactly the same, but with inf. So exactly the same, but with inf. Okay. So at this point, this object looks a little bit strange, but let me now define, give the assumptions on lambda. So we say that, so if I have enough space here, can you read if you write so small? Yes. Can you read? This is the definition. So I say that lambda satisfies the L condition. This L is in honor of Levinson. The L condition on I. So this is if every closed J contained in I, and for every I in J between 1 and n, we have so either this soup. Sorry. So there exist two constants, K1 of J and K2 of J, such that, now I have to change my word, such that yeah, I can start. So such that either this J is bounded and inf is minus infinity, or this the inf is greater or equal than K. So these are mutually exclusive conditions. They are a kind of dichotomy conditions. So we have either this or this. Now maybe it's not so clear what is the meaning of these conditions, but if you think to a little bit to the generic cases, this is somehow related to, in case of generic cases, to Stokes phenomenon. So these objects are objects which appear in the exponentials and determine asymptotic behavior, the dominance relations of vector solutions. Anyway, this is the definition. This was the preliminary. And let me say what is the main theorem that we proved. So given this differential ODE, and before it ODE, so I don't have to repeat, is our basic ODE. So given this ODE with decay conditions on R and conditions on lambda, let's say for lambda on the interval R, then there exists a unique, so this means unique, a unique fundamental matrix solution defined holomorphic. And unique means that it is actually uniquely specified by the following asymptotic behavior. So with asymptotics given by, so there is this exponential this Z naught is an arbitrary point. And here you have the identity matrix of dimension n, and this would be the solution to the unperturbed equation plus something which goes to zero. This is goes to zero, let's say in every, when for Z goes to infinity, in every age j. So the uniqueness means this little O1 is unique. There is no freedom here. Okay, so this is the main result. I will try to prove this, but I don't have time. The uniqueness of this little O1 is what makes the result different from the original Levinson approach. You fix A, so A is this one, you mean? Yes. You fix I, and actually, when you prove the theorem, you may need to make it a little bit bigger, but it's not important. I mean, you can fix A. That's it. Because here Z goes to infinity. So in every in every compact, well, if you take a J which is closed in I, so you have a little bit smaller. Yeah. Okay. For each of these J's, you can take your A and that's actually what this theorem says. Here, this A is not so important in the sense that Z goes to infinity, but if you want, you could put AJ here. I mean, in every time you fix a compact, there is a suitable A for which you prove the theorem.
And then the solution of uniqueness doesn't
No, it does not depend on it. Yes. If you have a comment, yes.
We have also in mind the possible situation in which we have a measure boundaries along with the profile. So you see, we already don't even assume that there exists an analytic continuation. Like the features around but it's really
So now I will not start by proving this theorem because maybe I cannot stop, I cannot finish, but at least let me, before I give example, say how this applies immediately to the cases 1 and 2, which are one motivation. So actually, okay, maybe I should not have erased the case here. This one is somehow the, well, no, maybe before I do this, okay. Some gradually. So how can we apply to our case 1 and 2? So these two cases can be studied reducing everything to some kind of model equation where lambda is as follows, is sum k from 0 to some integer h of some diagonal matrices lambda k, so these are diagonal, z to the sigma k minus 1, and these numbers sigma k are integers satisfying the following relation. Okay, these are integers. Okay, this is important. And our R of Z is for this specific case I'm going to consider is a holomorphic on it below. So in this case, no, sorry. Yes, I said they are real numbers. Real numbers. Sigma 0 is 1, so the leading term is constant, and then they decrease, and the last one is greater than 0. So between 0 and 1. So this equation, now if you compute what will appear in the exponent, up to a constant that I will not write. So the constant term, let me just skip constant term. Up to a constant, we can, and up to a partition, up to a permutation, we can partition this this matrix in the following way. So let me write and then explain. So when I write A plus B given two matrices, I just mean the block matrix, the block matrix like this. Okay. So this is a block matrix with which is diagonal. Each of these is the identity of dimension S, in this case S1, and S1 plus SL is N. Okay, and this Q, well, they are what you obtain by integrating here, but so up to permutation, we can arrange everything in such a way that these Qs are a sum of 0 to H of some constants, some kind of eigenvalue, some constants, lambda I k, sorry, qi. z to the sigma I from 1 to n. So if I consider the vector lambda I1, lambda I0, lambda I1 up to lambda IH. So this partition means that we are assuming here that lambda I is different from lambda J for I different from J from 1 to L. Okay, so we can always do this. Now I have so if we do this, now you see, if you consider the first values of lambda I0, lambda I1, and then lambda J0, and so, and you maybe there are some terms at the beginning which are equal for I different from J, but at some point they will become not equal because of this. So let me simply define Kij to be the minimum of values of k such that lambda ik minus lambda jk is non-zero. Okay, and let me just write this lambda I kij minus lambda j kij. Let me just define this. Let me call it lambda ij. Okay, so if I do this, I can introduce a generalized notion of Stokes race, which will be actually the things which will implement these definitions. So the Stokes race in this case, so the Stokes race for a pair I and J with I different from J are just the half lines of the C tilde star defined by, so you take, for example, the real part of lambda ij z to the sigma kij, and it put this equal to 0. And so, and to find half-lines, you have also to specify what is the imaginary part. The imaginary part of the same thing, for example, you take it to be less than 0. So this gives half-lines, and you can write exactly what is the argument of Z along this race. So you can write in the following way. So let me write first. So they are all of this form. Some tau ij, I will define it, plus 2 pi over sigma aij times m, where m is an integer. And this tau ij is just 1 over sigma aij 3 pi over 2 minus argument of lambda ij, where this is some arbitrary determination. So you fix one determination of lambda ij, and then you define this object, and then you just add multiples of 2 pi over kij, and you get all the Stokes race associated with the pair ij. So it's you see immediately that away from these directions, if you consider this qi and qj minus qj of z, when z goes to infinity, this will behave exactly as lambda ij z to the sigma kij 1 plus smaller terms when z goes to infinity. So this is the motivation to introduce the Stokes race, because they give away from the Stokes race the differences. This difference here depend on exactly on this. They behave in this way. Okay, so just one more thing before I can state the application. So the last thing I have to say is that now you can, if you take consider some real number such that this is different from all this modulo from all this determination. So if you take an interval eta minus pi and eta. Inside this interval, you have a certain number of determinations of argument lambda ij for I when I and j vary. Okay, and then if you just add multiples of pi, you get all the determinations. So let me call this interval here, I don't know, d eta. So now consider the argument lambda, all the determination in this eta. If you do this, you can consider the tau ij, which are sigma k ij, p pi over 2 minus argument lambda ij for the values of the determinations inside this interval. So the boundaries are not arguments of lambda ij. So they are enough to generate all the others. And these objects, which are directions of Stokes rays, are actually enough to generate all possible directions of Stokes rays. And we can enumerate them in this way, the partial order. Okay, we can give some names. So we have a mu values. Here we may have equality. We may have equality because we may have some tau ij, which is equal to some tau qp, even for sigma kij different from sigma kqp. So this is just a technical thing, but actually all these objects are enough to generate all the Stokes rays. And they are kind of basic Stokes rays. So these are the direction of basic Stokes rays. Okay, so now I'm almost ready to state the result. Maybe just one last remark. Sorry, this is a little bit technical. This tau ray, we have these Stokes rays which have lambda 0, 1, mu minus 1, like that. These denominators here, if tau j is a tau rho, so let me also call the corresponding page, let me call it sigma. So I can represent tau rho as 1 over sigma rho 3 pi over 2 minus some argument of lambda ij. Okay, so that's the last thing I wanted to say. Now, all the other Stokes rays can be obtained by tau rho plus some integer. These are all the possible directions of Stokes rays. Okay. So we have these Stokes rays. So now, there is one thing we may observe. So consider these objects here for rho from 0 to mu minus 1, which is the number of basic Stokes rays, and fix a mutable m1 and mu minus 1. Then consider this rays. So this rays will be somewhere. Okay, suppose you are lucky, you can find this m in such a way that this rays for a given m stay in a sector of amplitude less than pi. So if this happens, then we say that m is adequate with respect to tau rho to sigma rho tau rho, where rho goes from 0 to mu minus 1. So this is another more mathematically. This means that if you consider tau rho plus m rho pi over sigma rho minus pi, and then this interval tau rho plus m rho pi over sigma rho, and you take the intersection rho from 0 to mu minus 1. So let me give a name to this. Let me call it sigma m. So this means mu adequate means that this object is different from the empty set. Okay. So this happens in several cases. May happen or not happen. For example, just an exercise. If we are in the so-called generic case when this is different from 0 for every I and j, then it's okay. Let's say we can find adequate mutuples. Another counterexample. For example, if you consider the case when your interval, which I call the eta, contains only two values, which are in this case 3 pi over 2 and 2 pi, for example. These are determinations j, and you consider sigma 0 equal to sigma 1 equal to 1/2. In this case, so you have that tau 0, which is 2, so 1 over 1/2, 2 pi over 2 minus 2 pi, which is minus pi, and tau 1, which is 1 over 1/2, which is 0. So in this case, you have these two basic rays, which are tau 1 and tau 0, which are not in an interval in a sector of amplitude less than pi. And actually, in this case, you can never find an adequate mutable m. So this is a bad example. So suppose anyway, now, by the way, what? Oh, I have to hurry. Please to say what are the applications. Okay. So now the main theorem. The theorem I have stated in the beginning can be applied now immediately here. So under our assumptions, when lambda z is this sum up to k of lambda k z sigma k minus 1 with all the assumptions I made. So if m is adequate with respect to sigma rho tau rho, okay, then there exists a unique fundamental matrix solution, again holomorphic is holomorphic, and where with behavior again as before, so exponential of q1z i1 is1 q q1z ISL. This for z going to infinity, where this I is just let me say very right, sigma m plus pi over 2. So maybe it's better to explain with a picture. So suppose this sigma m, which is not empty, is an interval AM Bm. So indeed, A and B is not a good name. Alpha M beta M. So now, what is the half plane corresponding to this? Well, you have some direction. You take the direction given by Bm. You take the beta M. Take the direction given by alpha M. So your half plane is something like this. So if you want, you can say that you have actually an asymptotic behavior when Z is going to infinity in a sector, which is a sector Sm given by argument of Z between alpha M and beta M plus. Okay. So having defined this generalized Fock race under this condition such that we can find an adequate mutable, we can find a Greek solution and determine precisely what is the sector. Now, this can be applied, first of all, immediately to the equations we saw yesterday. This is very straightforward because the system of differential equations, I mean, the system we saw yesterday are a little bit simpler, but you can write this as some lambda k z to the beta k plus 1 plus r of z y. So in this case, it's just enough to do a change of variables. What is the change of variables? You have to put x equal to 0 plus 1, something like this. Sorry, maybe the opposite. No, it's okay. So this will reduce to the So the results you should see yesterday in, in your talk and Gabriele's talk about asymptotic behaviors. Actually, they are specified to subdominant solutions that we can do. Can be obtained from this model problem using this change of variables. And now, what happens for the ramified case? So in the ramified case, for a system with meromorphic coefficients, we can also apply the same result. Now, yes, I have three minutes. So let me go back to this was the motivation number one. So in this case, we know that we have a formal, so this is again holomorphic at infinity. And R is greater than 1. So we know that we have a formal solution. If you go to the paper of Balser, your catalyst, you have a standard way to write this. It's some kind of fine way to write this. This is a series with something like z to the n is an integer. Then you have a formal series, some fk z to the minus k from 0 to infinity. And this is a meromorphic invariant, just z to some Jordan matrix, some fixed matrix fixed by the equation, and some e to the q of z. Well, this q of z is again can be partitioned. And all of these qi of z this time are not like the ones I wrote before, but are something like lambda sum of lambda I k from 0 to r t minus 1, and I will explain what is p, z to the alpha k, where these alpha k's are just r minus k over p, and p is an integer. It's the ramification index. So if p is greater than 1, we have a ramified singularity. So this case can also be reduced to the problem, and then I finish. Can be reduced to model problem because, well, Maybe first let me just take the result so if I don't have to reduce it. So if you apply directly the model problem and use some gauge transformations, you can state the following result. So take a truncation of the formal series. Okay, this is a truncation up to some end. Okay, so then suppose that mu is adequate. And what does it mean now, adequate? Now, in this case, we have to define the Stokes race exactly as we did before, but instead of the sigmas, we have to use the alphas. So the Stokes race will be something like 1 over alpha rho 3 pi over 2 minus argument lambda algebra. So if mu is adequate for this Stokes race, which means that you can take basic Stokes race which stay in a sector of amplitude less than pi over r. So if you can find this adequate, then there exists a unique fundamental matrix solution, which is defined on holomorphic field with asymptotic behavior given by the truncation plus higher order terms, which are z to the n minus m minus 1 times g of z. G of z is this, the part with exponential. This is when z goes to infinity in a sector Sm, which is again written as before, but now is some alpha m argument of z, beta m. This time we have plus pi over r. So it's a sector of amplitude greater than, so we have alpha m, beta m, and a sector of amplitude greater than pi over r. So this can be obtained from the model problem. I will not do it because I have no time. Through a sequence of some simple gauge transformations involving the truncated series and involving essentially this part here. And then again by a kind of change of variables, which reduces the gauge transform system to the model problem. So I stress, just to conclude, that this characterization here, which is subject to this sufficient condition. So the system should be such that the Stokes race satisfy this condition for some m. So under these conditions, we can precisely determine the sector, which is this one, for any ramified singularity. Here we are in the ramified case, and we can prove uniqueness. Maybe I stop because I'm out of time. I'm very sorry. I cannot show you the proof of the main theorem, where you can see the main difference between Levinson proof and our proof. And this is based mainly on the fact that we have a wide half plane with L conditions, which are transversal. So a long lines transversal to Levinson only consider only sectors like this. So essentially only very, very small directions. And this is not enough to prove uniqueness.
Thank you. And also, any questions or comments? We have two questions. So in this case, so in this last case, how is the solution that you obtained related to the one obtained by multi-summation?
Is the same in the sense that if you have a specific differential equation. So I had some example to give, but sorry. Exactly one example of this. If you apply the standard procedure, case by case, you get the same.
What do you mean case by case?
If you have a general differential equation with general A, you have to actually work on it to obtain the formal solution and then prove and try to find what is the sector. In this way, we straightforwardly have a receipt which tells you just given this exponential, what is the sector. So that's the main theoretical advantage. We don't have to apply the procedure step by step.
And I have another question. So in the general case you consider, so how is the construction depending on the exponent sigma? So sigma are real numbers between 0 and 1 that you except sigma 0, you can move them a little bit, okay, without changing too much the stock phrase and so on, their distributions.
Yes.
So how is this construction depend? How does it depend on this choice of sigma? Can you?
No. Yes, that's a good question. So it actually depends in the sense that sigma. First of all, you have to consider the first case such that this is non-zero. Okay. This is what I call Kij, and then everything will depend on this sigma Kij. So depending on the values of sigma Kij, which on turn they depend on this. So depending on this, it may happen or not that you can find an adequate M. So everything is actually depending on sigma. I mean,
No, what I mean is that probably you have some values of sigma that you cannot move or something like this. But
the sigma are fixed by the equation.
No, but assume you want to see the dependence on sigma. So I believe that this condition, you say that some sigma are just at the boundary.
Exactly, they should not be too different from each other. Exactly. So to tell the truth, we did not study systematically the depending on sigma, but through example, you can see that if the sigmas are all very close to 1, there is no problem. When you can go away from 1 and you reach 1/2, and the difference you may have cases when you cannot find. But we did not study systematically a classifications in terms of
so which features of the sigma are they? You may have some chambers.
Exactly. Exactly. So we did not do this systematic classification, but it is exactly what happens.
Yes. Okay. Any other urgent question? Okay, then I'll send it again.